and this is Lab 3 for Physics 1, calculating the mass of a black hole. For this lab, we began with the goal of calculating the mass of an unseen object, in this case a black hole, that applies a gravitational force onto a star of known mass. This black hole's mass was randomly generated through code based off my unique Georgia Tech email address. For this lab, we utilized the knowledge of known quantities to find the unknown mass of the black hole. The star has a mass of 2 times 10 to the 30 kilograms. Our delta T and our lab code is equivalent to 1 Earth day, 86,400 seconds, and our gravitational constant is 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. Before we begin this lab, we first assume that the black hole that is exerting a gravitational force on the star is located at the origin. We're also assuming that there's only one force acting on the star. In other words, the net force acting on the star is just the gravitational force from the black hole. Some relative concepts that we will be applying in this lab are the momentum principle, parallel and perpendicular forces equations derived from the momentum principle, and Newton's law of gravitation. As I mentioned earlier, since the only force acting on the star is the gravitational force of the black hole, then we can use the momentum principle, which states that the net force is equal to the change in momentum over time, and set the change in momentum over time equal to the gravitational force equation, which is the gravitational constant times the mass of the star times the mass of the black hole divided by r squared, which is the unit vector of the distance between the black hole and the star. After some rearranging, we can solve for the mass of the black hole, in this case m2, to be equal to the change in momentum over time times r squared divided by the gravitational constant and the mass of the star. Using the starter code for Lab 3, I first entered in the initial conditions and the system property for the experiment. We're given the gravitational constant, as I mentioned earlier, the mass of the star, as I too mentioned earlier, and the time interval for the data points on the code is equal to 1 day, which is 86,400 seconds. Here, I applied the momentum principle into my code as I discussed earlier. Ultimately, I just embedded how to calculate dp from dv by multiplying velocity times mass. I set the net force equal to the dp dt, and I use the assumption that dp dt parallel plus dp dt perpendicular is equal to dp dt total, which is also equal to the net force total. To get the code to actually calculate the mass of the black hole, I simply embedded the equation into the code that we derived earlier from the gravitational law and Newton's second law. We have magnitude of the net force times r squared divided by the gravitational constant times the mass of the star. The magnitude of the net force is interchangeable with the magnitude of change in momentum over time, which is where we see Newton's second law applied firsthand. Here, you can see my code run calculating the mass of the black hole after each iteration to 1 Earth day. The arrows in the code are representative of the forces and change in momentums acting on the star. The purple arrow is the change in momentum over time in the parallel direction. The cyan arrow is the change in momentum over time in the perpendicular direction, and the orange arrow is the net force acting on the star. The perpendicular force on the star is what creates the star to change directions, causing the circular orbit, and the parallel force acting on the star is what changes the velocity of the star and the magnitude of how fast the star is traveling. To calculate the mass of the black hole, I pasted all the masses that were iterated by my code into an Excel sheet and calculated the average of all the masses of the black hole. The average mass of my black hole was 8.93 times 10 to the 33 kilograms. This lab assumes that by the momentum principle, the net force is equal to the change in momentum over time, and that the net force in the parallel and perpendicular directions is equal to dp dt in the parallel and perpendicular directions, respectively. Though these values are numerically the same, they do not necessarily mean the same things. Net force total, parallel and perpendicular, is representative of all the forces acting on the star, the forces acting on the star in the parallel direction, and the forces acting on the star in the perpendicular direction, respectively, whereas the change in momentum with respect to time is consistent with the speed and direction of the star as it orbits the black hole. Therefore, quantitatively, these values are equivalent, but qualitatively, they do not mean the same thing. Finally, in an alternate concept where our black hole was replaced with another black hole that did not change the trajectory of the star as it orbited the hole, does not have a new mass that could be calculated for. If the star does not change its motion at all, then this indicates that a black hole of the same mass was placed in the position of our previous black hole. Therefore, since gravitational constant, direction vector, and mass of the star do not change in this scenario, then the same value for the dp dt is also used, and therefore the black hole does not have a different mass to be calculated for than our previous one. A black hole of a different mass would yield a new dPdT for our star, which we did not observe in this scenario.